So hello everyone, today we are going to learn how to convert grey code into binary using ARM7 Assembly Language on the LPC2148 microcontroller in Keil Vision. Grey code is a special binary numbering system where only one bit changes between consecutive values. This reduces transition errors in digital systems. Now let us understand the core logic of grey to binary. Suppose the grey input is 1101. To convert grey into binary, we use cumulative XOR logic. That is, the binary bits are generated as B3 is nothing but G3, B2 is nothing but G3 XORed with G2, B1 is nothing but G3 XORed with G2 XORed with G1, and B0 is nothing but G3 XORed with G2 XORed with G1 XORed with G0. Now let's see the step-by-step mathematical conversion. Consider the grey data, that is 1101. So how to calculate B3? It is nothing but G3, which is 1. What about B2? It is G3 XORed with G2, that is 1 XORed with 1, and the result is 0. And next we have B1. To calculate B1, we need to perform G3 XORed with G2 XORed with G1. So the answer you get is again 0. Then we have B0, where you perform G3 XORed with G2 XORed with G1 XORed with G0. So the result you obtain here is 1. So the final binary output is 1001. So grey code 1101 corresponds to binary data 1001. How the ARM7 code implements this? Instead of calculating every binary bit separately, ARM7 uses a faster method. The original grey code is repeatedly shifted right and XORed with the current result. Each shift propagates grey bits into lower positions, and repeated XOR operations gradually build the cumulative XOR chains required for each binary bit. Now let's understand our code. At first let's check if this code has any errors. No errors, so we'll go ahead with debugging. Let's see what's happening here first. Area is an assembler directive which defines a section of memory to store this information. Grey to binary is the name given to that section of memory. Code indicates this section of memory contains instructions and read only because we don't want any modification to be happening to this particular code. Entry indicates where exactly execution starts, that is at the very first label after entry, and start, loop, stop are nothing but labels. End indicates the end of source file. At first we are loading our actual grey code into register R0. Let's see that happening. The same data is being copied to register R1 and we are performing our very first right shift operation by 1 bit position, and the answer we obtain is 6. After that we are moving the counter value 4 into register R3 because we are considering 4-bit data. The very first task we see is nothing but XOR operation between R1 and R2, and the result is stored in R1. Followed by that we perform our logical shift right operation, because of which R2 content will change to 3. Now we are subtracting R3 by 1 because one iteration is already completed, and if R3 is already 0, we break the loop. But that's not the case here because Z is still 0. Until Z is 0, this loop continues. Let's see what happens then. Again XOR, shift right, and the subtraction keeps happening until Z flag is set as 1. Okay, finally Z is 1. As soon as Z becomes 1, this particular loop is broken and we jump to an infinite loop. And now if you check the content of register R1, it is 9, which is our desired answer. That's all about this code.